Can you hear me? Is it on? Yes. Okay. Good evening, everybody. I'm Mattia Vaccari from the University of the Western Cape and the Inter-University Institute for Data Intensive Astronomy, and I'll be chairing tonight's session, tonight Cape Town time. So we will have first pre-recorded presentation by Jennifer Medina and Frederic Dauphin about Wide Field Camera 3 infrared blob classification with machine learning.
What we're going to be talking about is the supervised machine learning technique that we implemented in order to classify and detect these anomalies that are found in the Wide Field Camera 3 infrared detector. They're called blobs. This is on behalf of the Deep WFC3, aka the WFC3 Machine Learning Working Group, here based on the Space Telescope Science Institute. So just to give a quick recap, the Wide Field Camera 3 is one of the instruments installed on the Hubble spacecraft. It has two different channels that you can observe through, the UVIS channel being available for UV and visible wavelengths, and the IR channel being available for infrared wavelengths. The topic that we're going to be discussing revolves around the IR channel. And depending on whether an observer wants to look through UVIS or IR, the flux gets redirected to either of the two channels using something called the channel select mechanism, and that's what we're going to be talking about today. So the blob anomalies, these are small particulates that are actually found on the Wide Field Camera 3 channel select mechanism. And basically what these anomalies do is they block incoming flux from actually landing on the detector. So they manifest themselves as these little blob-shaped features of random size, and they're located in random spots on the IR camera. These are theorized to actually be pieces of cracked epoxy, this epoxy fluid that's basically holding the CSM together. And so the theory is that these pieces fall off of the hardware and into the CSM itself. And so that is basically what's blocking the incoming flux from bouncing off of the CSM and into the IR camera. So there's two reasons why it's critical to keep track of these blobs. The first one being that, as I mentioned before, because these pieces of cracked epoxy block light from actually landing on the camera, astronomers are potentially losing science pixels if these blobs aren't taken into account. And the second reason, which is the most important reason, is that because the theory is that these blobs are pieces of cracked epoxy, which is the material that's holding the CSM together, this might indicate that there's something going on with hardware and that the CSM might actually be compromised. So the way that we monitor for the blobs is through our QuickLook API. There are a couple plots that we use to visually inspect and keep track that there are no new blobs that came into the picture. And these plots are shown on the far left and the far right of this slide. So the blob image is basically on the left, what I described before as being like a blob map. So it's just spatially showing you where all these blobs are located on the image. And the image on the right is the blob difference image. It basically will only show the new blob if there is a new blob. And this makes it a lot easier for visual inspection because if there is a new feature, it'll be the only thing in the frame. And as you can see, to make the blob difference image, you just take the current blob image and subtract by a median stack of the prior 30 blob images. And so the theory is that if a new blob does show up on the current blob image, all of the prior located blobs will be subtracted with the median stack. So the only thing that you should see in the blob difference image is the new artifact. So the theory is that we would take these blob difference images and feed it into the model. And the model's prior knowledge of what a blob looks like would allow it to determine whether or not there is a new blob located on the detector. If there's a new blob, it would automatically alert the wide field camera routine. And if there's no new blob, it would continue the routine the next day. So because we're using supervised machine learning, we're working with two different data sets labeled differently. So the label of 0 will indicate a subframe with no blobs, and a label of 1 will indicate at least one blob that's found on the subframe. So before going into how we made these subframes, I'll talk a little bit about the data preparation. So we use pretty standard practices for data preparation on the IR full frame images. The first thing we did was outlier clipping, where we replaced all of the outliers that land outside of 3 sigma with either the minimum or maximum pixel value thresholds that we determined for that image. And then the next thing we did was feature scaling, and the technique we used for scaling was Z-score normalization, which basically replaces all of the pixel values with the number of standard deviations they land away from the clipped mean. And that is pretty much all we do to full frame. To grade the subframes, we first separate the full frame image between our training population and our validation population. So 75% of the image goes to training, the remaining 25% goes to validation. After we split up the full frame based on the training or validation, that is when we begin to diversify the data. And the first step that we do is we take random 256 by 256 cutouts or subframes of that region of the IR full frame. And for the blob images that are labeled 0, that's the point where we superimpose blobs that we generate from a randomly selected median stack from a single epoch. The next thing we do for both the label 0 and label 1 data is we add noise and a normal distribution with a spread of 0.75. And then for spatial awareness, we randomly rotate the cutout and do some random flipping. And that is what you're looking at in the GIF at the bottom, is several examples of subframes and what they look like. So now I'll leave it to Fred to talk about the actual model architecture and the results that we got.
Thank you, Jenny, for introducing us to blobs and talking about our data prep. As she said, my name is Frederick Goff, and I'm going to be talking about the model itself and then its results, and also going into some future work. So the model that we chose is called a convolutional neural network, also known as a CNN. And the reason we chose this because it's very good at computer vision and recognizing patterns in images. We build our CNN using 2 convolutional blocks and then 2 additional fully connected layers. So in our first convolutional block, we have our input image being 256 by 256, and we trained 8 filters to create these feature maps. So we have our first convolution using ReLU as an activation function, and then also doing a 2x2 max pooling to go from 256 by 256 to 128 by 128. We then do another convolutional block. Instead of having 8 filters, we have 16 filters, and then also doing another 2x2 max pooling to go from 128 by 128 to 64 by 64. And finally, we have 2 fully connected layers. The first fully connected layer being 65,000 neurons from 1 pixel of each feature map being a neuron, and then the second layer being 128 neurons. And then finally, we have our 2 output neurons of 0 and 1 for our blobs and non-blobs. So these are our results as a confusion matrix. We're getting around 1% accuracy, which is pretty good. And confusion matrix tells us what our model is classifying correctly, what it's not classifying correctly. So in the top left, we have our model classifying non-blobs as non-blobs 88% of the time. And our bottom right, we have our model classifying blobs as blobs 94% of the time. The top right is our false positive, or our non-blobs being classified as blobs. And these are caused by this phenomenon called dips. So sometimes when we're taking our blob difference image, it's actually off by a pixel or two. And instead of removing the blob, it's actually forming a shadow. And our model is classifying those as blobs. Our false negatives in the bottom left corner, or our blob subframes being classified as non-blobs, are images that are really just hard to classify. These should be images with a small blob, a faint blob, or a blob off the subframe. So to further motivate that our model is actually working, it's interested in blobs as a feature to use for classification, we use a method called saliency maps. So look under the hood and figure out what our model is interested in. So saliency maps will highlight the pixels that the model thinks it is extremely useful for classification. So on the left, we have an IR image around 2020, and it has one blob on it around 300 x-axis and then around 700 on the y-axis. And on the right, we have the saliency map with a completely black background except for one lit blob in the middle, indicating that our model is interested in those pixels for classification. So for some future work, one of the caveats we want to address are Earth and city lights. These have a different background noise distribution than our images that we trained on. So we're interested in seeing if these images generalize and we're still able to find blobs on these Earth and city lights, or if we have to go back to the drawing board and retrain our model. In addition, we want to implement into AWS, so being able to utilize cloud computing in order to train deeper models and get better results. In addition, some of our next goals are identifying numerous anomalies in WFC3, since we have dozens of them, and then also being able to take it a step further and removing those anomalies and getting science pixels back. Finally, this project is in support of the institutional goal of incorporating machine learning and data science into astronomical processes. Then the next decade, using these are going to be extremely important for analysis, so it's better to get ahead of the curve. But thank you for joining our talk. In our top right, we have a QR code of our report if you're interested in further details, but we will be available for questions. So thank you for listening.
Thank you. Have we got the speakers available on the line to answer questions? Yes, we do. So let me check the live questions channel for questions. I can't see any at the moment, so I'm going to take the liberty to ask one. Are there indications of likely or expected problems, arising in JWST imaging or spectra that you are considering, perhaps based on simulations and applications of your algorithms to those?
Sorry, could you just repeat that last part again, please?
Are you expecting similar or, well, unrelated problems that you could tackle with machine learning from JWST imaging?
Yeah, so that's kind of one of our bigger meta goals, is to work on these projects for HSC for future projects in preparation for James Webb, but also more specifically for Roman. I think one of the biggest challenges for Roman is the actual just pixel size. It's going to be around 300 megapixels, and doing traditional analysis on that many pixels and finding anomalies is just kind of out of the scope. So that's where machine learning can become extremely useful for doing those type of just super in-depth analysis that traditional methods wouldn't be able to handle.
I see, thanks. There's a question being typed, so hold on a sec. Still typing. Okay, so typing seems to be taking a bit too long, so perhaps you can take the question offline on Discord. So let's thank the speakers again, and let's move on to the next. to the next talk. So our next talk will be delivered by Ricky Osteen, remotely, and it will be about JDavis, an interactive visual data analysis tool for JWST in the Jupyter platform.
So as you just said, I will be presenting a demo of JDavis, an interactive visual data analysis tool for JWST in the Jupyter platform. To repeat what you just said, let me share my screen here. Just a moment. All right, hopefully you all can see that lovely opening slide. Now, to repeat myself again, just real quick, JDavis stands for James Webb Data Analysis and Visualization. This is a tool being developed by the Data Analysis Tools branch at the Space Telescope Science Institute in Baltimore, Maryland. And we are funded for developing this by the JWST project. So our primary mandate here is supporting the data analysis scenarios that are needed for James Webb, and keeping up to date with the pipeline development and ensuring that we can load and handle the data that will be coming out of James Webb. Now that said, we have been building this to be very general and support data from all sorts of different missions and instruments. And in fact, most of the data you'll see in this demonstration is not JWST simulated data. It's data from other missions. And so if you want to use this tool for things that are not JWST data, and it bothers you that the J in JDavis means JWST, I invite you to pretend that it means Jupyter instead for Jupyter Data Analysis and Visualization, because as you'll see, this is all very bound up with the Jupyter platform. Now, let me get rid of these slides and show you something more interesting, namely the application. So JDavis currently consists of 4 different configurations. These are sort of pre-built configurations to help with different modes of analysis. And the names are fairly self-explanatory. There's SpecVis, which is for analyzing spectra, CubeVis for data cubes, ImVis for looking at images, and MOSVis for multi-object spectroscopy. The first one I will show you is SpecVis, and the main way I'll be showing you how to use this tool is embedded in a Jupyter notebook. So this is my favorite way to use this tool. I think it's the most powerful because as you'll see, the application gets put right into the Jupyter notebook, and you can do more coding in the notebook, and you can also pull things out of the app and put them back into the app as you do analysis. So to initialize the application, first I just import SpecVis, my SpecVis helper from JDavis, and I initialize an instance of that class. And then by calling specvis.app, you will see an application now appears in my notebook. It is empty right now, which is not very interesting. So here I'm just going to grab an SDSS spectrum and use specvis.loadSpectrum, and you'll see the spectrum appear in my application. I'll take a quick aside here from this demonstration of SpecVis to talk about other ways to use this. You can also call JDavis from the command line. So you can call JDavis, tell it which layout you want, and give it a file name. And on the back end, this is using Voila, which is a package to render Jupyter notebooks as browser applications. And this essentially hides from the user that they're in a browser notebook. So if the user doesn't need all of that functionality of having a full-fledged Jupyter notebook, they can just pull this up as a browser app, and that kind of all gets hidden in the background. I mentioned Voila. I'll be trying to weave in, as I demonstrate this, some talk about the backend implementation of this and the packages we use. I'll also provide some links at the end to the repositories of all the packages. This is all built on open source stuff. This is all available on GitHub, all that good jazz. So to go over to SpecVis, again, looking at the application, I'll talk a little bit about some of the components of this application we see here. At the top, we have what I'm going to call the app level toolbar with things like tools to import data. This is relating to subsets, which I will talk about more shortly. In SpecVis, we have a slider where you can set the redshift, which won't do anything until I add some spectral lines, which I will show momentarily. And then perhaps most importantly, in the top right, we have an expandable tray that has some data analysis plugins in it. So these are things, a lot of this is hooking into like AstroPy capabilities on the back end for things like model fitting, or line analysis or smoothing data, doing things like that. And these are pre-built, but we hope, and the dream is that the way that you build these plugins is intuitive enough, or at least easy enough to learn, that users could even contribute their own plugins for their data analysis use cases. Going down to this section of the application, this is what I'm going to call a viewer, which isn't super relevant terminology right now because SpecViz only has one viewer. But the other layouts we'll see have multiple viewers, so that will become relevant later. If I click this data button, if I had multiple data sets loaded in, I could choose which are being displayed here. In this toolbar, I have things like panning and zooming. I can reset the zoom. I can zoom on either the X or Y axis independently. I can also always save out a PNG of what is displayed in this plot. So if I open that, drag that over onto the screen I'm actually sharing, you can see this saves out just exactly what is shown in this viewer. We don't claim that these are publication quality. That would be nice, but everyone has a different idea of what exactly they want their plots to look like. So we certainly don't guarantee you can just throw this right in a paper. I'm going to show two of the plugins here in SpecViz before I move on to QViz, and I'll talk about them just a little bit. I see a live question. The technology used to lift the app out of the notebook into a separate tab is called Voila. And again, I can provide links to those things in the future. And I hope that you're about to see that this spectrum graph is in fact interactive beyond just plotting, panning and zooming around. So the first thing I'm going to show is this line list plugin. I'll talk a little bit more about how these are coded on the back end and the package we use there when I get to QViz. But for now, I just want to show we have some preset line lists that come with the package. The user could also create some files to define their own line lists, or you can go in and create your own custom lines here. But for now, I'm just going to go into this common stellar lines list. And let's see if I can find them. I in particular want to look at these two oxygen lines, and let's just throw a couple more lines on there for fun. So now you can see overplotted on the spectrum, I have a few spectral lines. And this is where this redshift slider comes in handy. As I move this redshift slider, you can see the lines move as I change the redshift. So if I zoom in here a little bit, it's almost as if I've looked at this data before, and these two lines line up, if I can get it right, fairly well with these two emission features here. Now, obviously, there's only so much fine granularity you can get with this slider. You can also do things through the JDVit API and the SpecViz helper class, like setting the redshift from the notebook. I'm not going to do that now. You could also do things, for example, if you wanted to normalize this, you could pull this data out into the notebook. You could fit and subtract a continuum and then load that back in. That is useful for things like the line analysis plugin, where some of the things that automatically get calculated there are assuming a normalized spectrum. So if you don't have that, it won't crash on you. You won't get sensible values. The other thing I wanted to show here real quick, let me just go in and get rid of these lines because I don't really care about them now. So this is a good time on the back end. This data is being represented as glue data. So glue is a package for doing data representation in a way that provides some nice things in terms of defining subsets of your data and linking different data sets together. I'll talk about that a little more when I talk about InViz. But for now, the capability we're going to use that is relevant to that is selecting subsets. So I can select this X-range selector tool and say I wanted to fit this broad emission feature here. I could select a little bit of continuum on either side and select that. And now you can see up here in this menu that I talked about before on the toolbar, there's now a subset 1. I could create another one if I wanted to. I don't want to right now. So I'm just going to select subset 1. And now on the back end, the glue data structures now have this global sense of this subset 1. So if I were to go into the model fitting plugin, for example, I could select my data. And here I could say, I'm only interested in fitting subset 1. So when I go to fit this model, it will only fit within those bounds. I'm gonna just select a constant because the background looks pretty constant there, and select a Gaussian and add that. And then I wanna tell it, I wanna add those two model components together. And then I can click fit. And hopefully we can see it did a pretty decent job of fitting that. I will make that line a little bit bigger so it's more visible to you. So I haven't clicked on this tab yet. This is options for the plotting, just in terms of things like increasing the width of lines, changing colors, things like that. And here you can also see the model has been added to the data. So I can get rid of my actual data and just show the model. You can see it fit pretty well. And we can do things like go down in the notebook and call specviz.fitted models to see these models we've fitted. So we can see exactly this is our result and pull that out into the notebook. We can also do things like get the spectra from the data. And specifically here, I'm going to grab the spectrum for subset 1. And you see this automatically gets translated into a specutils spectrum 1D object. And this has a mask applied to it corresponding to the subset that we've defined. So I hope that shows just a quick taste of getting things in and out of the app and a couple of those plugins. I'm going to move on now and show one of the other layouts. So this is CubeViz. Here I've already started the application and loaded some data. So this is a manga data cube. And you'll see here, things look a little different from SpecViz. So here we have 3 image viewers, and then we have a spectrum viewer. This spectrum viewer in CubeViz and also in MouseViz is essentially just SpecViz dropped right into this CubeViz. So everything you saw in the SpecViz demo also applies here. I could add spectral lines and things. The only thing I don't have is, instead of a redshift slider up here, instead I have a slider to slice through this cube. And on the image viewers, I could also do things like change the scaling to make things look a little bit nicer. I can change to a different color map, all sorts of great stuff like that. This is probably a good place to mention. So Glue is the data on the back end. And then in order to link up the Glue data on the back end with this, this front end, which is built on IPyWidgets largely. So IPyWidgets is providing things like sliders and all that nice stuff. There are also some in-between packages called Glue Jupyter and Glue Astronomy. So Glue Jupyter is just connecting Glue data structures on the back end with this whole framework in the Jupyter notebook. And Glue Astronomy provides some astronomical data specific translators to go between things like the specutils spectrum 1D object I showed in SpecViz and the backend Glue data. As a part of all of this, Glue Jupyter has 2 plotting backends that are available. So one is Matplotlib, which probably most of you are very familiar with Matplotlib, but we actually use the other one, which is called BQplot. I believe BQ is because it was initially developed by Bloomberg. So it's probably Bloomberg quantity plots, something like that. Doesn't matter. The moral of the story, this is BQplot on the back end, and that is handling things like the browser canvas rendering and JavaScript and all of that, and exposing in Python a lot of plotting classes for things like the 1D profile plots, the image plots, tables, and we subclass those to provide a little bit of extra functionality specific to us. And I'm sure there will be questions about why did we pick that instead of Matplotlib, which astronomers know and love. That decision was before my time, but I am sure that at least part of it is that some of the contractors who work with us are some of the main developers on BQplot. And same with Glue Jupyter and Glue Astronomy. So we have a very direct line to, if we need things or if we need features that aren't there yet or are buggy in the underlying packages, we have a very direct line for a lot of that to the people who develop those, which is, as you might imagine, a very big advantage for when you're developing an app like this. So let's see, what else did I want to talk about in CubeViz? I thought this would be a nice time to talk about yet another backend package. So I'm going to open this Collapse plugin. I'm not actually going to use it right now. just to note, you can use this to collapse your cubes along whatever axis you want, and perhaps selecting a spectral subset. But I mainly just want to look at this and show how we build this plugin. So we've got some descriptive text. We have a link to the documentation. You can select data. There's a button to actually apply this to your data once you have everything set up. I'm going to go over to the code here. So the way we lay all this out, and I find this very nice because I am not a front-end coder, but we use the Vue.js and Vuetify.js framework package, what have you, on the back end. And there's a Python package called IPyVuetify, which allows us to use this easily in Python. And this does some very nice things that I will show here. So the concept I'm showing here, this is a Vuetify template file. So this is defining what this plugin looks like on the front end, the user, what they're going to see. So this is called collapse.vue, is just the name of the file. You can see there's things in here, we're defining rows and columns. This vSelect is a drop-down menu. So this is hooking into the data items that are available in the backend and keeping track of which you have actually selected. And these, and the other thing I'll mention in a moment, these are actually variables in the Python file that corresponds with this template file. So I'm specifically, going to talk about that apply button. So if I scroll down here, we wrap this in our custom little tooltip class. So when you hover over the button, there's an informative tooltip that tells you what it does. And then there's a V button. This is just a Vuetify button class with our accent color, which is orange. The text is apply for the button. And the important thing here that I wanted to show is that this @click behavior, so this is what happens when we click the button, this just is labeled collapse, which is not super informative, except that in our collapse.py file, what happens is, so our class for our collapse plugin, subclass is this template mixin, and it loads that collapse.vue template file. And what IPyVuetify does is it connects these two files, and any variable, any method that is named in the Vuetify template file. So for example, that collapse method that happens when you click the button, in the Python file, it knows to look for something called view_collapse. So in the Python file, anything named view underscore what have you is, that corresponds with something in the Vuetify template file that is corresponding to an event or something displayed on the front end. So when I click that button, it knows to go to view collapse and execute all of this code in the Python file. And it's very easy to link things between the back end and the front end. Now, hopefully I can actually get out of this full screen view. There we go, great. And let's see, I have about 7 more minutes left to leave a little time for questions. So I'm gonna move on with our whirlwind tour here to the other configurations, just so I have the chance to show those. So I will move on to ImViz. Here, you can see by default, I have one image viewer. Now I said that in QViz, the spectrum viewer is basically a full-fledged SpecViz dropped into QViz. The image viewers in QViz and MOSViz are not yet fully fledged ImVizes dropped in there in the same way. That's something we're kind of moving towards, but ImViz is a little more different and complex than the other configurations, so it's a little more difficult. And part of that is that we are trying to make ImViz sort of fully featured in comparison to things like DS9, and making sure we get the functionality that you would expect into this configuration. And it's a little hard to get all of that into the other configurations without overloading things. Now let's see. First of all, I'm gonna say I have 2 images loaded here. These are Hubble ACS images, I believe. And I'm gonna make them slightly more exciting to look at. You may have seen nothing changed there, and that's because in this layer tab, I had the one that's on the bottom selected, and it's covered up by the other. So there we go. That's a little more interesting. So this is intended to be nice for looking at images, doing quick look stuff, and comparing images. So you can see as I move my cursor around, up on the toolbar, if I take my cursor off the image, it goes away. But up on the toolbar, you can see the pixel coordinates, the value there, and the world coordinates as well. In addition to this, I can press the B key and blink between these two images. And you can see here, this is where I'm going to talk a little bit about the glue data linking on the back end. These images are currently linked by pixel, and there is some distortion, dithering, what have you going on. So as I blink between them, you can see they don't line up exactly. If I want them to line up exactly, luckily, I can go into the plugin tab, and the only current plugin for InViz is this links control. So I can instead change from pixels, which is sort of the default for performance reasons. I can change that to a WCS link and either do a fast approximation or something more exact. Fast approximation is pretty darn good. And I can click link, and that recreates the glue links between these two images on the back end to correspond to the world coordinates. So now if I blink between the two images, you can see all of the stars are perfectly lined up because we have linked by world coordinates instead of pixels. Also in InViz, I can add more viewers. So if I want to view these side by side instead of at the same time in the same viewer, I can do that. And I'm just going to have to change the stretch again real quick. So you can see here, now they're side by side. And if I want to pan and zoom both of them at the same time, I can select this linked panning and zooming tool. And now, as I do things like pan and zoom around one, you can see the other one stays in sync. And that's all enabled by that glue linking on the back end and the way we're representing the data and the fact that this knows that these share a WCS solution, which is rather nice, I think. If there's anything else here, right. We can also select regions. So if I wanted to tell the application I was interested in that star, you can see that region also gets duplicated on the other image because again, they're linked by WCS. And there are lots of other tools here. You can use the mouse to adjust contrast and bias. I'm very bad at it, so I'm not going to show that right now. Again, you can save out images. You can blink from this toolbar, although it tells you there's nothing to blink right now because I'm showing them separately, not in the same viewer. Yes, that is just a quick demo of InViz. Let me move on to MOSFiz before we are out of time. So this is for doing multi-object spectroscopy. And this is the one place in the demo. This is actually a simulated NIRISS dataset from James Webb. So you can see here, I have an image viewer. I have the 2D spectrum, which will be a little more obvious if I rescale this, that it is a 2D spectrum. There we go. So you can see that's a 2D spectrum. I have the collapsed 1D spectrum, and then I have a table of my sources that I can page through. So here I have about 40 sources. I will note we've done a lot of work recently on increasing performance here. Previously, I think this data set took like 10 minutes to run, and as of now, or to load, 10 minutes to load into the app. Now it takes about 8 to 10 seconds, which is obviously much better. It was painful before. So kudos to everyone on my team who worked on that. And here I can click around the table, and you can see when I click the table rows, that data gets loaded into the viewers. I could also, so I don't have to change the scaling every time. I can click this button up in the toolbar to lock those display parameters. So as I click around, this actually stays useful. A couple other things I will note is that for this NIRISS data set, all of these objects are actually on one very large image. And so as I'm clicking around on the table, it's actually based on the world coordinates are in deck in the table here. It's actually zooming on this large image to each individual object. So you don't have to find them yourselves. But if you want more context, you can always zoom out. And I think the last thing I will highlight here in MOSFiz before I am done is that, again, because of the linking in Glue, if I pan and zoom along the x-axis of this 1D spectrum, it knows that these share that wavelength axis and it keeps them linked up. So I've hit 25 minutes. I think I will stop there in case there are questions. And thank you so much for listening to my talk. And actually, before I end, let me just show real quick. I do have a slide calling out that we have had just a ton of people contributing to this. This isn't even the complete list. I think I got everyone who's contributed code, but there are many more people who have tested this feedback. And I also have a slide with the links to these packages that I mentioned. I can post this after the talk in Discord. So thank you very much.
Well, thanks, Ricky, for this very engaging demonstration and for the impressive tools that you've been developing. I see some typing on the live questions, although that has not come to fruition as yet. Perhaps I'll ask a question which you might have discussed during the demonstration. But are there ways, to query existing archives, for your favorite objects, directly through JDavis, or do you need to provide them, with existing FITS files in order for them to run? Can you actually query archives and download them on the fly?
That's a great question. So from within JDavis, there's not a way to query the archives. So you have to bring your data to JDavis. However, and I can't believe I forgot to mention this. So I mentioned running it in a notebook. I mentioned running it as a browser app. What I forgot to mention is that in the MAST archives, I'll actually share my screen again here real quick. So the MAST team at Space Telescope is working on integrating this directly into MAST. So while you can't query JDavis, you can't query archives from JDavis, from MAST you will be able to open up data straight from the search tab. The intent is you'll be able to open that in your browser in a JDavis instance. So the intent eventually is that if the data from your search in the MAST archive is compatible with one of the JDavis configurations, you'll be able to click a button right here and it'll open that new data in a new tab and load it for you right into JDavis. And lots of people at this conference have talked about the fact that we're going to have just absurd amounts of data from these new missions and how to get the analysis up near the data instead of PIs needing to download the data themselves and do it locally. So this is kind of part of that intent, is that that analysis could be done up on the cloud next to the data instead of having to download everything yourself.
Yes, I can very well imagine that will be incredibly handy to a lot of people, even just using, the huge legacy of Hubble at this stage. Thanks. Now we do have a couple of questions on the live questions channel. So perhaps you can, pardon me? Michelle can ask it live, I suppose, if she's around.
Thanks very much for where do I look? There. Thanks very much for the really great talk. This looks pretty cool. I guess the advantage of embedding visualization inside a Jupyter Notebook is that you can obviously do some stuff before you visualize data and then do some stuff afterwards. So I was just wondering kind of how easy is it to actually extract things from the visualization? And the one example I thought of is like selecting regions in an image, for instance, and exporting that to a data frame or doing something with it.
We're trying to make it very easy. So I showed a little bit in SpecViz of that, in that you can always call specviz.get spectra, and it will output everything as Spectrum 1D objects. And as part of that, if there were subsets defined, it will apply mask to that automatically. You can also always, there's an app level API method that I didn't show called get data from viewer and get subsets from viewer. So if you're only interested in the subset definitions, you could get those out. And I think we may translate those to AstroPy regions, or we can, or leave them as blue subsets. There's no option to get things out automatically as pandas data frames, but you could do that in the notebook after you got the data out. And then the load data methods into the application, you can pull things out, do things with them, and then load them right back in, is intended to be very easy.
Cool, thanks.
Thank you for the question.
Right. There's now a number of follow-up questions, and I'll ask them in the order they were asked. So Mark Taylor is asking, how performant, scalable is JDavis for dealing with large data sets, e.g. large images?
It's hopefully okay. large data sets means something different to some people than it might to me. So I got very scared when I heard the phrase 350 gigabyte PITS file mentioned earlier in the conference. So I can't make any guarantees or estimates how performant it would be with an image that large. I think the images I was showing are around 150 or 200 megabytes maybe. So we haven't done stress testing on the level of some of these next generation missions that are going to be happening, but we have been doing our best to make things performant. I don't know if that's a Weasley answer or not, but that's my answer.
Yeah, I suggest that along with the several other questions, I mean, you take this up on the specific channel, I mean, for the questions after the end of the talk. But let's thank Ricky for his talk. And in the interest of time, we'll have to leave the questions, I mean, to the Discord channel. So let's move on to our next talk that is going to be delivered by Peter Williams, and it's going to be about interactively visualizing massive images and catalogs in Jupiter with the AAS Worldwide Telescope. So here we'll talk about large images.
Hi, hopefully you all can hear me. Thanks for this demo, and this will tie in nicely, I think, with the one that came right before. And to give you a little bit of context, I'll be talking about things that are very similar, visualizing large data in Jupiter and Jupyter Lab. I'll try and emphasize some of the differences just to give my perspective on things, but also I want to point out that Worldwide Telescope, which I'll be talking about, is a visualization tool in GLUE, and we're in communication with GLUE Jupyter folks and JDA Viz folks, and I think there's a lot of synergy in everything that's going on right now. So I'll start sharing my screen, and hopefully you can see a blank browser window, and please yell at me in the live questions if you can't. And I'll start by, so you can follow this demo yourself. I have a Jupyter Lab environment and Binder Hub, which I'll start loading up, and should load up pretty quickly because I've been testing it. And so I want to give the context as Worldwide Telescope has had similar kind of Python visualization widgets, as you're seeing now. And I've been thinking for a while, I've been kind of frustrated with the user experience that we were presenting, and also thinking about kind of how to approach things in a way that was really the best for the way that Worldwide Telescope works. And what Worldwide Telescope can really do well is I think of it as exploring your data, sort of putting something in its context astrophysically, dealing with large data sets where you don't necessarily know what you're looking for. It's not a tool that's necessarily aimed at like nitty-gritty fine-grained analysis of individual pixel data, but can do things like help you visualize your 50 gigabyte images or things like that. And when I was thinking about sort of how to make this work as well as we could, I realized that the whole widget model of you start up a kernel and you create a little widget object, I mean, that works very well, but it's kind of limiting in especially the kind of user experience that I want to deliver. And so what we designed pretty much at the beginning of this year was a new approach, which I call the application approach, to contrast with this widget approach. And there's a poster that John Griffey has made. I think it's X03020, which talks about that a little more. So here in our Jupyter Lab environment, you might notice there's this big button that says Worldwide Telescope. And if I click it, we open up our application in its own little tab. No, I haven't even started a kernel, no Python, no nothing. This is a freestanding web application, which happens to be embedded in Jupyter in this case, but I can just open it in a separate browser tab. It's detached from Jupyter in that sense. It can be run on its own, and I think that's actually a very important engineering factor for allowing this app to be used in a wide variety of situations. So our default interface here is kind of a little Google Maps for the sky sort of interface, and always point out I'm sharing my Zoom session without the video optimization, so it might look a little bit choppy for you, especially if the bits are traveling across the Atlantic Ocean. But it's a very smooth interface, which I think works really well. I will start up a notebook here, which is called AAA ADAS Focus Demo, which will show some of the new features that we've added recently. So the way that I usually like to set things up is I'll open up a notebook, I drag it side by side and maybe collapse this little pane. And we have a nice, nice side-by-side interactive data visualization setup, and I haven't even used my keyboard yet. So the way that we work in this environment is the Python kernel can connect to the app, and this ends up being a lot of the engineering behind this app is running in JavaScript in my web browser. This kernel is running behind some proxy somewhere in the cloud, and routing communications between the two ends up being complicated. And a lot of the effort is not just building the interface, but actually getting to the point where these pieces can talk to each other with the right data, getting the right place at the right time. So I'll just run these Python commands, which will sort of set up our default interface. And so we have, these user interface elements are built using the JavaScript Vue library. And, we've got a bunch of built-in backgrounds. And so I'll switch to PanStars, which is hosted very kindly by Space Telescope. And so this is an all-sky mosaic of PanStars 3Pi data release 1 data set. And if I zoom in, you'll see the data tile in. And you'll see a nice depth of everything that's going on here. So to start talking about the new features that we've got recently, the first one I want to show is with NSF funding, we've developed a feature to allow us to visualize huge FITS files. So as an example, if I run this command, it will essentially tell the application about a data set. And then I can click through here and load up this data set. And this is a mosaic of data from HyperSupremeCam provided by user El Sayad. And so this is a FITS file that is, I think, 20,000 pixels on the side. And hopefully you've seen a little bit. If I zoom in, we're getting the Google Maps effect of my data actually tile in progressively. So this whole data set, I think, is tens of gigabytes. But I can explore it in the sort of, interactive Google Maps-y, panny-zoomy way that you'd like. And the key to this is you need to process this data set to sort of downsample it and also break it into little pieces so we can load data on the fly as opposed to having to navigate the whole data set. So this interface over here provides some basic controls so I can do the usual stuff. You'll have seen these color map names before. I can play with this stuff and a little bit of a thing where I need to adjust this UI over here so I can expose some controls. So I can adjust the stretch and the zoom. So I'm interactively doing it at the sort of fully zoomed out level. And then if I zoom way in, we can see the data adjust here. And so the way these controls work is I click on this little target icon and there's sort of a usual little motion that if you move it to the left, it will move the value lower. And one thing I want to show is that's genuinely useful here is if I get my cutoff just right. So there's actually a sort of waffling pattern. It might be easier if I switch it to logarithmic. There's a waffling pattern in sort of the low-level flat fielding here, which I'm having trouble pulling it out now. But you can actually see it in this sort of high-level summary view. And if you're looking at your FITS file in little individual tiles, it can be sometimes hard to pull that out. So I'll talk a little bit more about how we process the data to be able to visualize them in this way. But I want to emphasize that, in order to provide this interactive, rapid data exploration in Jupyter, we need to be sending little pieces of data over the web. So you need some kind of data processing. It might be on the fly, it might be in advance, but you can use HTTP range requests, but if you want to show sort of the thumbnail of your whole image, you have to compute that thumbnail somehow. And if it's a giant, 20K by 20K image, to compute a fair thumbnail, you have to do some kind of advanced processing in order to extract that. So besides big imagery, we can also now deal with huge catalogs. So one of the other features we've gained is dealing with progressive HIPS catalogs. So something like the Gaia DR2 catalog has been in the same way that this image is tiled and broken into downsampled versions and small pieces. The HIPS progressive catalog standard defines the same sort of thing for catalog data. So I can run a command here, which will load up a catalog and command the app to start overlaying data. So you'll see the little circles appear as we fetch catalog data and zoom in. And likewise, we have some basic UI controls here. So I can say, change the color that we're using to display this catalog or whatever else I might want. And I can tweak the point sizes. And we also have some really cool infrastructure that lets this app, which is, it's actually running on a separate domain actually from the MyBinder, transmit data back and forth with Python. So if I run this command, it might take a little while. Okay, not so long. We've pulled in the data, the points in this viewport, and transferred them from, again, the JavaScript running in my web browser through the Jupyter server to the actual Python kernel, which is running somewhere in the cloud. I've got a nice table of all the Gaia information about this. And I can, we don't have to use these progressive catalogs. I can then just example upload my own table. So I'll just put this table back here and say if I hide the Gaia data and fool with this a little bit, you can see this is sort of my custom catalog, or if I zoom back out, it's just that rectangle where I pulled in data from a particular viewport. And you can do things like you can click on a source and we'll also pull up a little bit of information there and let you set it off to a Ned query. So to get in a little bit more detail about the imagery, which I think is where we've got the most exciting stuff happening, I'll just temporarily get rid of this and zoom back out. So this is a image that we've already done this tiling process to break it into little pieces for efficient serving. We've also put a lot of effort into building the technology to be able to get do this in your Python kernel and get it into the app. So if you think about this, maybe my kernel is running in the LSSD data center, the Rubin data center, and there's some image there which I want to visualize. My app is fundamentally making HTTP requests to retrieve those data. And so I need to process this image and then somehow make it available through the Jupyter server. And that turns out to be, there's a bunch of pieces that have to come together now, and I'll kind of walk you through those pieces. But fundamentally, it's something that, once those pieces are in place, it seems to work pretty reliably. So this example, we use a FITS file from the VLA Sky Survey. So this is a quick look image, and we'll show here that it'll download. It's something like a 60 megabyte, 53 megabyte FITS file. And so, if I just want my web browser to load this all at once, it can do that, if you have a fast internet connection, but that's a little bit big to sort of send right into the JavaScript all at once. So we have a JavaScript package called Toasty, a Python package called Toasty, which deals with the data processing, which takes a big file like this and transforms it into what we need to do the interactive visualization. So the pieces here, this is some code which essentially, Toasty is a very pluggable kind of framework, which lets you specify a lot of different things. Because this demo is running in this Binder Hub environment, where it's got a very low memory allocation and only one CPU, we're not going to do anything very ambitious, but we'll show kind of the contours of what's happening under the hood. So I specify how I'm going to save my data. I specify the way that the data are broken up, and in this particular case, I've transformed the sample data set into something using a tangent projection, which makes it a little bit more efficient to process. And so this just sets up the variables that say how we're going to do everything. The first thing we do is we sort of figure out how it will eventually all land on the sky. And in this case, that computation is trivial, but we have more complicated processors that will, if you have a bunch of different images, each with their own arbitrary WCS, you got to sort of figure out how to get everything on the same grid. So the first thing we'll do is we'll take the source image, which that one's only about 3K by 3K, and we'll break it into a bunch of little tiles individually. And so that's pretty just, we're taking a big data array and pulling out little postage stamps and writing them all to disk. And then we call the cascade stamp is taking those and then averaging them together. So a quartet of 4 tiles gets spatially averaged into a bunch of 2 and do a single tile. And then we write out a simple kind of index file that describes the overall format and contents of the data set. So this is all running on, this Binder cloud computer somewhere. And it turns out, so if I want to make data available from the Jupyter kernel to the web browser, there isn't a lot of, you can't really do it until now. So we've developed this tool called the Kernel Data Relay, which kind of wires together kernel to Jupyter server to browser. It ends up being a surprisingly subtle engineering challenge, but I think we've got a good solution now. And so in this case, the command that I'll run explicitly essentially does the stuff to inform the app about the data that I've made available. And now I can click on this image and pull it up. And so this is this VLA image. And it took me a while to talk through all that, but you'll notice that there was no creativity or interactions involved once the recipe was I was just talking through it. So this can run quite quickly. I've just been talking my way slowly. And I see a question in the live chat asking about how we interface the front end JavaScript and the back end Python. So the Jupyter environment or the Jupyter framework provides this comms system so that Python can talk to JavaScript elements. So what we do is we have a set of messages that are JSON structures that you can send to the app, which fundamentally is done using web post message events. And essentially the Python code generates these messages and sends them along to the app. And so the Jupyter Comms interface is just a simple message transport system that allows us to do that. So the main thing is like the app that I have running in, I can open up the app in a separate window, and this app has nothing to do with Jupyter, but it can still receive these same kinds of messages and be controlled in the same way. And, I pulled up some documentation here where, all these messages are defined and their fields are spelled out. And so you don't need to stick to our implementation to control what's going on. But fundamentally, this approach, most of the stuff that's actually at the Jupyter level is kind of setting up pipes for these messages to go back and forth properly. That's the wrong image. So I can do similar kinds of fooling around with this image. The radio sky looks pretty different, but I don't know. I know that this is on top of NVSS, so we can pull up NVSS, the old VLA sky survey is reference imagery, and I can say blink the image on and off, and if I zoom way in, this is what the NVSS had, and this is what the VLA sky survey has. Same instrument, but different configuration, different spatial resolution, makes a pretty big difference in how things go. And if I say, compare back to Pan-STARRS again, it's pretty impressive that, the radio sky, the radio sources and the optical sources, say the two radio sources that we've got on the left side of my screen here happen to correspond to, these optical, it looks like some kind of galaxy cluster. But other than that, you have a lot of stuff where the connection between the radio and the optical is just surprising. Or I think one of the ones that we've got down here, yeah, you can see something that seems to be shifting right here. So we've got a nice little example of, in the optical, we've got these two objects that are probably just unrelated next to each other. This one's much brighter. And then if I bring back the radio, we see that this one is actually the radio bright object. And if I pull up the Gaia catalog again, it will eventually pull in the data from this. And you might not be able to see it, but there's a little source there. And if I pull this up in Simbad, I can see that it's a Sloan quasar, which makes a lot of sense. And likewise, so I can pull down the sources that are in this field of view right now using this table object that I created before and get the Gaia information for the things that happen to be in this field of view. Yeah, so, and then if I zoom out, sort of watching all the Gaia data as you navigate around the sky, I think it's just super duper cool. Yeah, we stream it all in as it's needed. And if I hit this, we can go back and seek back to my VLASS image. So those are the things that have really changed, where we've always been able to do basic fits images, but sort of loading them all as an integral file, and really to deal with large area images or large number of pixel images, you have to do this tiling or some kind of on-the-fly data streaming step. And we've got all the pieces in place where we can do that with a variety of of kinds of data, and it all works really well. And we're using WebGL2 to accelerate, playing around with the data and rendering it and everything. And so it's just a really smooth, slick interface, and it really lets you just see what's in your data, do a kind of quick look sort of interaction in a way that is not what you always need, but when you need it, I think we can do a really good job of it. The last thing I want to show as an example is I've tiled some of the data sets from the Hubble Panchromatic Hubble Andromeda Treasury Program, FAT. So if I pull this up, so I've got the Andromeda Galaxy in 2 different filters, not the entire FAT data set. Each one is something like 27 gigabytes of data. So with the initial cuts, you can't really see much, but let me just get rid of the stuff that I don't want. Get rid of the, sorry Gaia, sorry sources, sorry Glass. So if I fool around the cutoff here, this is that FAT file, and I don't know, I'll full screen the app, and if I control click, I can rotate the view, and we can maybe have our fun magma view. And I'll say that these sort of chunkiness elements are in the data files that I used, and not part of our data processing. So, if I want, I think this is really great. You can zoom all the way, zoom in this far and slowly see all of these bajillions of stars show up. So I see a question in the live chat about you showed a Gaia overlay while zoomed in. Can you view the full catalog if you're zoomed all the way out? Yeah, so the way this progressive, I'll just add that back so I can also add it through the UI. So we have a built-in list of, no, Zoom is getting in my way. Let's move that. We have a built-in list of a whole bunch of catalogs that you can choose from. So the way that it works is essentially the more zoomed out you are, the more it truncates the fainter sources. So there's kind of a spatial sorting of the data, and then there's also a brightness sorting of the data. So that, if I'm out here, if I loaded every single source in this field of view, it would be probably like millions, but we truncate it. And then when I zoom in, you'll see that it'll pull up more data, and probably we'll get some more circles appearing. Brian asked about the kernel data relay. Yes, it's, I'll type in the link, but yeah, all of this is open source. And what I've discovered is that, to make this really like full Jupyter Lab network environment work, there's a ton of pieces that have to be involved. We have multiple server extensions, we have lab extensions, we have the PyWWT Python package that runs in the kernel. So our GitHub organization has like 50 repos, but everything that you're seeing here is on GitHub. There's a couple of fixes that I haven't merged to master yet, but it's all open source. Thomas asked about, or Thomas asked how long it takes to compute the tiling for the FAT image. I think that ended up, once I worked out all the bugs in the data processing, that ended up being sort of like 8 hours parallelizing. So you might have noticed in what I've done here, there's a parallel thing, which because we're running on this little cloud instance, we stick at 1. But for instance, we have the engineering work done in Toasty to be able to parallelize over things. So on my laptop, I can parallelize over 16 CPU cores. On the Harvard cluster, I can farm the job out to 100 separate nodes. So there is an overhead, and for FAT, for that large quantity of data, it can be substantial. What I found actually was that, so we use the reproject package for so we need to get everything into a common WCS TAN projection. And FAT comes in like 25 or so data bricks of a few gigabytes. And then when reproject wanted to process those, the memory usage would be like 30 gigabytes. It ends up being pretty RAM intensive, and we have to kind of chunk up the processing a little bit to avoid blowing things up. So I think we're doing pretty good, but I suspect that, doing that projection with a package like Montage or something would probably be a lot more efficient. But fundamentally, it's you map everything onto some kind of tangential projection. You have it a power of 2 number of pixels on each side, and then you just pull out little 256 by 256 rectangles. I see that my time is, I guess while I'm at it, my time is almost up. While I'm here, it is kind of fun, so I can also like add, so this is the other image, and I can do like maybe make this one white to blue, and make this one white to red, and set the opacities, and we can get some kind of little color information from the view that we've got here. Yeah, so this is, we do have to transform the data, so you're not looking at the raw fits data in a certain sense. That's kind of the price you have to pay for this interactive user experience. So depending on where you are in kind of the data exploration versus nitty-gritty data analysis, spectrum of needs, this might not necessarily be what you need. But I do really like, it does do that exploration well. And I think this idea of this kind of app, which again, I can run it in a separate window. I don't need a kernel. I can kill this and my app is still happy. I think, although now I won't be able to tile in new FAT data because I need to pull the data from, or I know I will because that data is off the cloud. I think this sort of paradigm really unlocks a lot of superior user experience options that when you're kind of in the widget paradigm become really tricky to implement. So I'm pretty excited about doing more of that. And I'll be answering questions more in the dedicated channel for this. Code is open source. I can help you process your data. I'm just really excited to see what people do with this. I hope you're excited too. And I'll stop my share there.
Thanks, Peter. I guess you took care, within your allotted time, you took care of most of the live questions, so that was extremely effective. We got a couple of minutes though, so if somebody can think of something, I'll ask one in the meantime. So we've been talking about massive images and about some, you showed some radio images. I wonder if you've ever thought about incorporating 3D cubes, such as the ones that are going to be coming, from future interferometers, for instance.
So cubes are definitely, it depends on your needs. Like, there's some kinds of cube analysis which fundamentally I think are going to be real challenging to implement in our kind of Google Maps sort of paradigm. But like I just showed very quickly, we can do things like load up fat imagery in 2 bands and switch between them very quickly. And so I think if you can sort of frame a problem as 10 or 20 or 100 or maybe even 1,000 different images that you're kind of scrubbing through, I think we can do that well. So for instance, kind of time domain, getting multiple visits of, from LSST or whatever it might be, scrubbing through those, I think we'll be able to do very nicely. If you're kind of wanting to be able to rotate that cube in a certain sense, that's where our data model, you're probably going to need to use an app that's really designed for that, because our data model is more like a stack of 2D images. And for some applications, that'll work great, but for some applications, that's going to be limiting.
Of course, thanks. Great stuff. So I guess we can, we're right on time. So I guess we can move on to the next and last talk of the session. So I'd like to welcome Simon O'Toole, who's going to be talking about FAIR standards for astronomical data. You're on, I think. No, we can't hear you actually.
Okay, can you hear me now?
Yep.
Good. Sorry, I can't see if I'm on or not. Okay. Okay. Oh, now I can see you.
Although we can't see your slides at this time.
Yeah. Let me try again.
Yeah, let's do that.
Now you should be able to see it.
Yes.
Okay, good. Okay, so today I'm going to talk about FAIR standards for astronomical data. So I'm Simon O'Toole from AAO, now part of Macquarie University, and in this talk I'm mainly talking about things to do with the Data Central project. And I'd be very remiss to not mention the funding agencies that support us and supported this, the work that went into this. So first of all, what are the FAIR principles? So the guiding principles were set down actually in around 2014 for scientific data management and stewardship, and then published in Nature by Wilkinson et al. In 2016. So you're probably all very familiar with the 4 key pillars of FAIR, that data should be findable, accessible, interoperable, and reusable. So I'll talk a little bit more about what those principles mean in more detail now. So data is findable. These are the actual principles, so they are a little bit dry, but very basically they're talking about discoverability, how easy is it to find your data, and not just the data, but metadata that describe it, and that these metadata should be rich. They should provide a large amount of information about the data, including things like how it was taken, what it is, and how it was processed. They should have some kind of identifier that's globally unique and persistent, and they should be in some kind of register resource that's indexed so you can easily search it. And so really you can think about this part of FAIR as how easily can your data be discovered. So you'll see a lot of synonyms in this talk just to try and get the point across. Accessible. Now this is something we heard a little bit about accessibility from a web point of view earlier. However, accessible here doesn't mean accessible to someone who has a sensory impairment, but it really means something, some standard way of getting the data. And it may be that you have some authentication and authorization because you're not ready to make the data fully open yet. But at the very least, the protocol and the way that you actually get the data is open and free, and anyone can come along and implement it. And then a key part of this part of the FAIR principles is that metadata should stay accessible even when the data that they describe are no longer available. And this is actually one of the challenging parts of the FAIR principles. So here we have how easily can your data be obtained. That's they're the simplest way to think about these, as I said, quite dry principles. So interoperable, we hear a lot about this word. This word gets used a lot, but in the FAIR principles, it has a very specific meaning, and that is that the metadata in particular that describe your data use some kind of broadly applicable language that represents it. So something that is used across all of the data sets. So something is only interoperable if everyone is doing it, if everyone is using it. So this language, and then also a vocabulary. and that they follow, the vocabulary also must follow the FAIR principles. So it also must be findable, accessible, interoperable, and reusable. The metadata should also include qualified references to other metadata. So that could be within a data set, or it might be across multiple data sets. And this is also one of the challenges that we in Data Central have found. So how, and really this is how easily can your data be compared? Because if you're not using the same language, you cannot compare your data with other data of the same object or the same thing, same things. And then finally, reusable. So there are, this is really where it comes down to having a good number of attributes that describe your data to make things very, very clear what it is that you've measured, and how in some ways you would like people to use it. And then it also discusses things around the usage license. So this could be something like the Creative Commons license, of the various kinds of Creative Commons licenses, but it could be any number of licenses. And then probably the most important, I think, here is that the metadata should include detailed provenance. So how the data was processed, not just I took this data with this telescope, or I took this data, I ran this data through a supercomputer or something like that. But you know, what was done to it after that? Was it processed? Was it analyzed? How did you derive the data that you're presenting to the user? And then metadata should meet the domain relevant community standards. So really, what this thing is not just, you know, how easily can it be used, although it is that, but how easily can your data be trusted? Because that is a really key thing when you're sharing data, and you want people to compare your data. Trust is an essential thing, and that's a whole other talk for Core Trust Seal and those kinds of standards. But for FAIR, the reusable part is really about that. So why would you make your data fair? So FAIR principles make your data more valuable. That's a really, really key thing. But by more valuable, obviously, I don't mean a monetary value. I really mean more useful, more, and this comes to the comparable as well, I think, and more trusted. If your data is usable and trusted and comparable, then more people will get value out of it. They will be able to compare it with their data. And then obviously, this is in some ways an obvious one, I suppose, but it will be easier to find for all researchers. And this is a key thing. If people can't find your data in a relatively straightforward way, then they're not going to use it. It's going to disappear into the ether, never to be seen again. And then, you know, we all, you know, if you're a researcher and you need to publish papers and you need to get grants, then you need to have your data cited. And this is becoming more of a key thing for data to be cited as well. So it's easier, it's more valuable, easier to find for researchers, and easier to combine and integrate with other distributed data sets, because it's very easy to have data set in one location or in one sort of platform. But if you want to compare it with someone else's data in someone else's platform, then making your data fair is the easiest and best way to do it. And really, it also encourages more people to get involved in STEM. And this is a really important thing in this day and age. And so, for example, if you make your data accessible and easier to find, then you get programs like Zooniverse. You get programs that allow members of the general public to access your data, to find your data. If you go to the Zooniverse website, there are so many programs, so much data that you can find very easily because it is accessible and discoverable. So I'm just going to touch very briefly here on something that the Go FAIR website calls the faiриfication process, how to make your data fair. And so I find these kind of workflows useful, but a little bit complex and a little bit jargon heavy, because I don't know what a semantic model is. I think of a data model. But really what you need to do is get the data. If you want to make data fair, you get that data, you have a look at what the data is, and then you model it. You create a data model, and then you try and work out what the linkages between the different data that you might have are, and then other data. And then number 5 there is a key thing: assign a license to it so that it can become open, and then you define the metadata. But that's part of the data model to me. And then you deploy it. Very, very straightforward in concept, but can be quite difficult. So really what you need to do is how well do you understand, what you need to ask is how well do you understand your data? So in astronomy, we've been leading the way in this space for quite a long time. FAIR is in large part addressed by the IVA, and I'll talk in more detail about that. And particularly if you look at its architecture note. So there is an architecture note that's publicly available, but version 2 is out soon, and that's what you see here in this diagram. And so basically, if you look at the diagram, you see sections that are starting to sound familiar already, because you have a core part of the virtual observatory here in the middle, but around the outside you have terms like finding and using, getting. So this is and sharing. And so these are these are synonymous with find, findable, accessible for getting, interoperable for sharing, and reusable for using. And this has been the core of the IVA architecture since day one. So there's a lot of similarities. The one key difference between the IVA architecture that you see here and the FAIR framework is that IVA focuses on the processes to move the metadata and the data through some kind of architecture, rather than the properties of the source or data themselves. However, they're so closely aligned that with only a small amount of extra effort, you can make the next step to become FAIR, and I'll discuss that in a little bit. So there are a few specific principles that the IVA standards don't provide because they're out of scope, and I'll talk about those, or only recently implemented. So just to look at how the IVA architecture sits on top of this diagram, you have different components. You have data formats and data models, you have semantics, you have query languages, and these are the core things that really help the finding, using, getting, and sharing of data. And so you have a registry that allows discoverability. You have data access protocols that allow the getting of data. And then you have applications that allow you to use it. And you have the actual data itself, the collections of data that allow sharing. And then these are just the protocols. All of the protocols up to now for the IVA, and you'll hear plenty about that throughout this meeting. Various IVA protocols, and then if you come along to the IVA Interop, which is next week, you'll hear even more and some of the details of how to use them and how they're developed. So in brief, the IVA standards and protocols address all but about 4 of the FAIR principles. It's easy to discuss what they don't cover than what they do, because there's only roughly 4 that they don't cover. And of course, these non-IVA based principles can still be met. You just need to do a bit more work if you've already implemented a TAP service and a simple image access service and those kinds of things. So I'll skip through these quite quickly. The IVA standards are mainly findable. The FAIR principles require that metadata are assigned a globally unique and eternally persistent identifier. So IVO IDs, which is a commonly used ID within the IVOA, is not easily citable, and so a lot of people are obviously starting to move to DOIs, and they're not required to be eternally persistent. And this is often a challenge because of funding. It's very, very hard to demand that. Also, the standards don't require that the data identifier be returned in all cases. So if you do a query to an IVOA compliant system, you don't necessarily get this ID, and there's no requirement. And so the principle is really left for the service providers, the people who are implementing these IVOA standards, to decide how they're going to address it, or if they're going to address it. And the standards are mainly accessible. Metadata are accessible. This is the requirement from FAIR, even when the data are no longer available. And the IVOA doesn't specify any rules on how reliable the service must be. However, they do provide regular weather reports. If you come along to the interop meeting next week, then you'll hear some from the operations working group. And once again, this is left up to the IVOA service providers to determine how to manage this requirement. And the standards are basically interoperable. You do have to do a little bit of work here, but it's really once you implement the IVOA standards, you're basically there. You're basically at interoperability. They implement vocabularies, and in particular, they have a language, the Universal Content Descriptors, and there's a version of that that's out, UCD 1+ at the moment, and that means that the principle is fully met. But if you really want to get sort of into the nitty gritty, then to really meet the interoperability principle of FAIR, you need a cross-referencing framework that goes beyond just the data that you have. So data link in the IVOA is a protocol that basically links data through the metadata within a data set. So you may have spectra and images and data cubes and catalogs that describe an object or objects. But really, in order to be truly fair, you need to have that same data link standard go across multiple data sets and potentially link into other data centers, other places that store the data. And they're mostly, almost, but not quite fully reusable. This is just from a standards point of view. There are no specifications from the IVOA about what license data and metadata should have. But many funding bodies are starting to require or request that groups who are holding data apply licenses to data releases. And for example, our funding, one of our funding agencies is the Australian Research Data Commons, and they are starting to request it, and very soon they'll start to require that there are licenses attached to data before they support any more projects. But it's up to the providers, once again, to determine the best licenses to use. And often this is then pushed onto the data producers. So the survey teams, for example, or the researchers, or the whoever it is that's producing the data needs to decide on a license. And I'll also note that while we now have in the IVOA the provenance data model, the provenance DM, it was only published last year, so there are still many systems that don't yet implement it. So now I'm just going to talk very quickly about a case study, the All Sky Virtual Observatory, which is five nodes. Part of it, really, this is the Australian Virtual Observatory, and there are 5 nodes: the Murchison Wide Field Array, the Theoretical Astrophysical Observatory, SkyMapper, CASDA, which includes the ASCAP archive, and Data Central, which is the one that we've built, and that includes the Anglo-Australian Telescope archive. Very briefly, so the MWA is one of the SKA pathfinders in Australia. It's a low frequency radio telescope, and it has, in fact, much more data than this now. They're butting up against their 40 petabyte quota of data. And it's it has a very large amount of data, and mainly provides the pre-processed uncalibrated data. but it still runs a TAP service and uses the OBSCOR data model. TAO, the Theoretical Astrophysical Observatory, it hosts simulations for galaxy formation and cosmology. It has over 1,000 virtual universes, and it doesn't really have, it's not particularly virtual observatory compliant at this point. The SkyMapper node is specifically built supporting SkyMapper, which is a 1.3 meter telescope at Siding Spring Observatory. And the goal is to have a digital record of the entire southern sky, multi-epoch, 6 filters processed and calibrated with the data made available. They have a simple image access service, for example, a TAP service, and they have around about a petabyte of data that's made publicly available. And they have a data rate of 100 megabytes per second. CASDA, which is run by the CSIRO, and that is basically the ASCAP, the Australian SKA Pathfinder Science Data Archive. So this is similar to MWA. It's one of the SKA precursors, and it provides science-ready data products. It's been running for a few years now, and they've just had a whole lot more data released, processed data. So I definitely encourage you to check that out if you're interested. And then finally, Data Central, so operated by the AAO, or now AAO Macquarie. We run a lot of virtual observatory protocols, and we also make use of them, not just providing services like simple image access, spectrum access, data link, and TAP, but we actually have applications that consume other virtual observatory services from other systems. We also host the AAT Data Archive, which has 40 years of data, going almost but not quite back to the beginning of the telescope in 1974. And it's heterogeneous survey data that should be, and we don't just have optical data, but we have a growing amount of non-optical other wavelength data. And we provide API and UI access. So the ASVO, a couple of years ago, we surveyed all of these nodes to try and gauge how well they met the FAIR principles, and we found the results here at this table. And so you see that for most of the principles, we hit them pretty well. That's the Y in this table is yes. The P is a partial or under development. And so here we really see that the main roadblocks for the ASVO nodes are the principles that we discussed, that I discussed earlier, that the IVA standards don't meet. And that's because most of these nodes actually implement the IVA standard. So TAO at the end here is a little bit different, but they have their own way to be findable and discoverable and meet the various requirements. The interoperability here is really a question of provenance. How well do you track your provenance? And that's where that's under development. And so and some of the data link implementations, but these are well underway, and they're probably at this point, some of these may be a little bit out of date, in fact, but they're very close. So certainly Data Central now implements UCDs and data link. So the key takeaways from this talk, and this is something that I can't emphasize enough, I've probably already talked about it a fair bit. If you implement the IVA standards and protocols to provide access to your data, then you'll be almost, but not quite, fair. And then with just a few extra additions, you can become completely fair. So I talked about those, and really they're things that are becoming more standard in a data set. So it's like a key thing is really the licensing issue that I talked about, but also the digital object identifiers. So something that is eternally persistent. A DOI lives forever, even if the data doesn't. So you can if you define a DOI for your data set or your data, then that will live on even if your data center or the data repository disappears. The metadata that describe your data will persist, and that is one of the thank you. That is one of the key things that that make your data compliant with the FAIR principles. And so then let me just go back a little bit here. So yes, and then if you one of the things I think is a challenge moving forward, and this is going to be very difficult, is this cross-referencing framework. So using a protocol like DataLink, but basically saying, I have this big catalog of data, I need to cross-match it with someone else's big catalog of data. And this is sort of some of the things that we'll hear about at this meeting and at the IVOA meeting next week. How do we go about doing this in a timely manner, particularly because there's more and more data coming online. So you have LSST, you have SKA, these very large data volumes coming in. How do you actually provide this cross-matching and cross-referencing in a timely way? There's some of the challenges that we have moving forward. As I said, licenses, but provenance. And I think provenance is a really, really important thing to cover as well, and especially for the SKA, because the SKA isn't going to store the absolutely raw data as it comes off the telescope. It's going to be pre-processed before it even hits a data center. So understanding the provenance, tracking that is really, really critical to make the data fair. Because as I said, after all, this is really about making the data trustable. How well do you trust the data that you're querying or searching, or how well do you want someone to trust the data? Think about it from that point of view as well. So really, the absolutely key takeaway is to make your data virtual observatory compliant today. There are a lot of tools out there that will make this easy or straightforward. Basically, there are TAP services that you can just download and deploy. Multiple data centers now have implemented their own and make them publicly available. There are simple image access. There are simple spectrum access. So it is now far easier than it ever has been to implement the VO standards, the IVOA compliance standards. So I'm going to end there and say thank you for listening. And I want to pay special thanks to James Tocknell here at the AAO. He was the one who put together a lot of the survey work around the ASVO that I've presented here and was funded by the Australian Research Data Commons. And then, of course, a special thanks to everyone at the ASVO nodes who cooperated with James, took the time to answer some of the questions that he asked around the fairness principles and allowed us to get a good picture. And I dare say there are a few more talks later in the week about FAIR principles at other data centers, and I dare say you'll hear some familiar things on how to implement and what work still needs to be done. So I'll leave it there. Thank you very much.
Thanks, Simon. So we've got a couple of comments on the question, on the live questions. I guess there's a poster about best practices in data publications that is also relevant to FAIR, which you might have a chance to see out here and on GatherTown. And then there was a question by Francois. I'm not sure you addressed it. I mean, by going back to some of your previous slides about for interoperability, do you think better integration of data models in VO service could help?
Yes, I do. These are complex systems now, but I do think that, yeah, I think the data models can provide a lot of help there. I mean, they're sort of the fundamental things that underpin all of FAIR, really, and that's why they live in the VO core. So yeah, I do think that if we have I don't want to say improved because they're already very good, but if we enhance the data models to take into account some of these the UCDs and that metadata, then I think yes, absolutely.
Thanks. So we are a bit over time, so I think let's thank all of the speakers from the session again. And I'd like to remind you that we now have a Gather Town poster viewing session, for the next 60 minutes, so you'll be able to gather there, over the next hour. And I remind you that we start again tomorrow at 8 o'clock South African time or 6 o'clock UTC. Thanks, everybody. See you tomorrow.